Everyone, welcome back. In this unit, we're going to be talking about flooding. And in particular, we're really going to be focused on precipitation-driven flooding. So when it floods because it rains too much. In our previous lesson, we made some mention of floods that might be triggered by tectonic events. So if, for example, an earthquake burst a dam and that caused a flood as all the water from the dam rushed downstream. In this unit, we're going to be focused more on floods that happen because it's been raining too much or there's a lot of snow that has melted, those type of flooding events. That's what you see in the background image here. This is a flood along the River Trent in the UK. The river should be just a tiny little blue stripe down the middle there, but you can see it has really overflowed its banks and affected a lot of people there. So we're going to learn a bit about how that kind of thing might come about. So our goals for this lesson are first for you to appreciate the variability of the natural world, then to understand how floods are measured and to use that to calculate flood risk to particular locations, and then finally to evaluate some of the methods we have for reducing the risk that people face from floods. So to start off, I want to make the point that nature is variable. So natural systems, even when they're in balance over kind of the long time scale, they're going to exhibit significant variability on scales ranging from day to century and everything in between. So things are not going to stay exactly the same within a natural system. And we see an example of that in the data that's shown at the bottom of the slide there. That is rainfall at the town of Bungaree in Australia. And so you can see how we can calculate the average. That's the line that goes across there. We can average that together. That's the average rainfall. But you see there are very, very few years over the century and a half almost that data is covering where the actual amount of rainfall they got was at that average. Most years were either well above or well below that average. And so from year to year, that could change dramatically. You have a year with way above average rainfall, followed by one with way below average rainfall. And so that kind of variability is present in all kinds of different natural systems. If we're looking at pre-industrial societies, in really general terms here, these are big picture generalizations, but pre-industrial societies tended to find ways to adapt to this variability. They would figure out a way to organize their society that they could handle the fact that next year might be an extremely wet year, next year might be an extremely dry year. They couldn't predict which. Next year might be really cold, might be really hot. They couldn't predict which. And so they had systems to adapt to those changes, to deal with the variability in the system. As we moved into industrialized societies, like the one that we live in currently, those societies need consistency from the natural environment in order to maximize their efficiency. So if you're going to maximize the total output of, say, grain that you're growing in an area, in order to do that the most efficient way, you can't have the rainfall change dramatically from year to year. You can't have the temperature change dramatically from year to year. So industrial societies really want to even out that variability, make the natural world less variable so we can efficiently maximize our productivity. So we might do something like building a dam so that we can hold back the water when there's too much and let it out when there's not enough. And so we even out the amount of water that we're getting on our farms rather than adapting to the fact that we might get a lot of rain or a little rain from year to year. So industrial societies really want to smooth out, flatten out that variability. And yet, sort of ironically, industrial societies often are causing the environment to become more variable because we have much greater anthropogenic impacts on natural systems. And those impacts can have a lot of unintended consequences that create forms of variability that we weren't planning on dealing with. So we have this kind of ironic situation of industrialized societies want nature to be very consistent and not have a lot of variability, not have a lot of change year to year, decade to decade, etc., but end up actually causing lots of variability to happen. So Here's an example if we focus in on the issue of stream flow. So stream flow is one of those factors in the Earth system that can have a lot of variability, that can change quite significantly, even just over the course of a year. So the data that we were looking at on the previous slide was the total rainfall for each year. Each bar represented a year. But the water flow in a river or stream might vary dramatically just from one part of the year to the next. We might have a big dry season, wet season difference with big changes in the level of water in that stream. And when that happens, societies and ecosystems may come to actually depend on that variability. They may need those changes happening. They may need to be there to be an alternation of, high stream flow and low stream flow. But an industrial society may try to control that variability and in doing so create unintended consequences. So the example that I want to talk about, and which is depicted on the screen there, is the example of the flow of the Nile River. So you probably know a little bit about the Nile River as being the sort of heart of the land of Egypt since ancient times. And the Nile River has a very variable stream flow. It has one part of the year where it rises really high and another part of the year where it drops really low. And so for millennia, the people living along the Nile have adapted to those changes and have even become dependent on those changes. So in ancient Egypt, you had farmers living along the Nile, and they would move out away from the Nile and let the floodwaters rise. And then when the floodwaters receded, they would go back to the places that they lived right along the river, and they would find that their fields had now been watered. The water had, from the high level of the river, had soaked into the ground, and so that provides moisture for their crops in a desert environment. And the river also deposited a whole lot of silt on the field. So that river water is not pristine, pure, and clean. It's bringing with it a lot of dirt and stuff that it has eroded upstream. And when it floods, it leaves some of that behind on the fields, but that becomes fresh, new, nutritious soil for people to grow their crops on. So every year, this variability of the river, the rise and fall of the floodwaters of the Nile, would water and fertilize everybody's fields. But as we get into the 20th century, Egypt begins to industrialize. And an industrial society doesn't like dealing with that kind of natural variability. Wants to be able to even out so that we have a consistent stream flow in the Nile all year round, because that makes things more convenient for navigation on the river. That the size of the river is going to be the same for boats going up and down at any time during the year. For industries that need to use that water in whatever manufacturing process they have that were being built in Egypt. And for farms to be able to very carefully control how much water they were taking and putting through their irrigation canals onto their fields, rather than having to hope that they get the amount that they want from the flooding of the river. And we were building a lot of infrastructure near the river that could potentially get damaged or destroyed if the flood level of the river was particularly high or had a particularly high amount of silt in it that can wreck buildings and roads and so forth. In ancient times, your road was a little dirt path. It wasn't a big deal if it got covered in silt, and your house was like a hut that you probably rebuilt every few years anyway. But if we're building modern style buildings and roads, those will get a lot more damaged and be more expensive to replace. So the government of Egypt built what you see in the photo there, which is the Aswan High Dam. So this is a big dam in the southern part of the country, and it was built to regulate the flow of the Nile River. So it holds back the water when the stream levels rise, and then lets it out when the stream levels are low, so that you get a consistent water level in the Nile River downstream of the dam. So it eliminated that cycle of flooding, made the river much more consistent and reliable, took that variability out of the equation. So that was all well and good, except that also had unintended consequences. So one of the things that now meant was that farmers along the Nile River were no longer getting that silt deposited on their fields by the flood of the river. It was no longer bringing fresh soil to their fields. And so over time, their fields would get worn out. All of the nutrients would be used up from their soil. And so those farmers had to turn to artificial fertilizers. They had to purchase fertilizers to put on their fields because it was no longer getting fertilized every year by the flooding of the river. And those artificial fertilizers on their fields would then wash off into the river. And then the river now had this artificial nutrient boom in it that led to big blooms of algae. And so we started to get these harmful algae blooms and a kind of a dead zone forming, because when we have an algae bloom, that uses up all the oxygen in the water and kills off all the other aquatic life. So we got a bunch of unintended ecological and socioeconomic consequences from trying to even out that natural variability in the water level of the Nile River. Okay, so to talk about flooding, we want to start by talking about its opposite, which is drought. So flooding, we've got too much water. Drought, we've got not enough water. And when we talk about drought, there are several different ways that we can define a drought. So several different kinds of drought that we might be in at a given place in a given time. So the first kind of drought that we might experience is a meteorological drought. So meteorology is weather. So this is a drought defined in terms of weather. So that means reduced precipitation. So if you were to look back a few slides at that Australian rainfall data, look at some of those years where the bar was very short, we had reduced precipitation that year, those years would be meteorological droughts. So if we just have not as much precipitation as we normally get, then we could be in a meteorological drought. If we're in a meteorological drought for long enough, we progress into a hydrological drought. So hydrology is water systems. So when we're in a hydrological drought, we have reduced water storage in reservoirs and aquifers. So if we have just like 1 year of very low rainfall, there may still be plenty of water around for everybody to use because our reservoirs are still full from the previous good rainfall years. Our aquifers underground have been charged up. They have a lot of water that has flowed into them, so wells can pull that water up easily. You know, the soils are not totally parched. There's still a little bit of moisture in the soil. So we can kind of compensate for not getting a ton of new rainfall if we've had some good years previously, and so water is stored in these other stocks within our hydrological system, right? We're thinking about the hydrological system, meteorological drought, we're slowing the flow from the atmosphere to our surface water and groundwater, but if those stocks are still pretty big, we don't have an immediate problem, but as those stocks start to drain down, and they're not getting refilled, they're not getting that flow from the atmosphere to rebuild them, and we're still drawing down that water. We're still taking it to use for drinking and industrial uses and for plants to grow and all those kind of things. Then we're entering into hydrological drought, where our water storage, our stocks of water that we draw on start to drop significantly. And if our hydrological drought goes on for a while, we can progress into socioeconomic drought. So when we hit socioeconomic drought, we're now experiencing the impairment of human activities. So now our hydrological drought is severe enough that it's starting to really hurt people, that people are starting to suffer negative consequences as a result. So our social and economic systems are being affected by the drought. And so some of those activities that might be impaired when we get into a socioeconomic drought are things like drinking and cleaning. We don't have enough water to do all the things we'd like to do. People have to start restricting their uses of it for these kind of household uses. We might start to get crop failures. We don't have enough water in the reservoirs to irrigate our crops, and so they're not growing as well. The plants are dying or just having their yield drop. We have reduced water for industrial uses. A lot of manufacturing and industrial processes use a ton of water for cleaning things, for transporting other chemicals as a solvent, for cooling uh, machinery that builds up a lot of heat, etc. Data centers these days use a lot of water to cool all of those computers that are running at a high rate to process all of our computer requests. And so if we don't have a lot of water in the reservoirs, in the aquifers, etc., then that may compromise those industrial uses. We may see intensified pollution in the water that we do have. So if we have less water in the river, but we still have the same amount of pollutants going into the river from whatever sources are pumping pollution into the river, there's less water to dilute that pollution. So the level of pollution in that river, so the average amount of pollution in a given volume of water, is going to go up. The water quality is going to get impaired. If we're still producing all the pollution and we have less water to mix it in with. And we can get degradation of soil. If soil is dried out for too long, then that soil can become harmed. It can build up things like salt in it that then create long-term problems for using that soil for things like agriculture. So we have these different stages that drought can go through. That we start with decreasing that flow of water into our surface water and groundwater stocks through reduced precipitation, and then that progresses into significant reductions in those stocks, and then into impairment of the human activities that depend on getting water from those stocks. So then if we go the opposite direction, we have too much water, then we're risking floods. So a drought is usually a slow onset hazard. A drought is not going to start overnight because we're talking about reducing certain flows, and it's going to take time for the impact of that to be felt in some of these very large stocks of water that we have. That's why we have this progression from meteorological to hydrological to socioeconomic types of drought. So droughts tend to come on slowly, and it takes a while for us to realize and be really sure that we are, in fact, in a drought. Floods, on the other hand, tend to be very rapid onset. So a flood can come upon you with very little warning. So you might have just hours or even minutes between when a flood is detected and when it comes to where you are in a flood risk location. So floods can come on very quickly. And so with a flood, we're dealing with two things that can cause problems for us. So on the one hand, we have the water. So a lot of the problems from floods are because there's too much water. There's water in places where we don't want it to be, where it isn't normally found. But then we also have the energy that that water comes in with. So as water is flowing down some sort of a stream and at high levels, creating a flood, it's coming in with a whole lot of energy, right? We've got a lot of kinetic energy as the water's moving down that stream. And so that energy can be as dangerous as just the pure amount of water. And the picture there is from a flood that happened just a few years ago in the town of Harmony, not too far south of us in Slippery Rock. So along Connoquenessing Creek that flows through Harmony, there was a major flood, and you can see a lot of the people living close to the creek saw that floodwater come way up into their yards, into the lower levels of their houses, and it did a lot of damage to those people living there. So some of the main effects that a flood might have, the first and most obvious one is drowning. If you are caught in a flood, you can just get pulled under the water and die. And usually that's a result of that energy, because if the water is just slowly rising around you, you can usually get away from it. But if it's coming in with a lot of force, a lot of energy, you can't get away from it. It may kind of grab onto you and pull you under. That's often what happens to people if they do drown in a flood, is that the force of that water sucks you under and prevents you from getting away with it from it, and that's when you would drown. So that's the most obvious immediate effect. But you also have people and property swept away by those flowing waters. So lots of stuff gets washed downstream by a major flood. Again, that's the energy of the water flow that's doing this damage. So it luckily didn't happen here in Harmony, but some places where there's a major flood, houses will actually get pulled off their foundations and float down the river. And even when it's not that strong, other things, cars get washed away, dumpsters get washed away, trees and logs get washed away. And so that does damage to wherever that thing was taken from. If your car's been washed away in a flood, it's probably totaled. You're probably going to have to get that replaced. So that's bad for you. You've lost your car. It's also bad for anything that car hits as it goes downstream, because now it's, nobody's driving that car. It's going to slam into other cars, other people's houses, trees, infrastructure, anything else that the flood crashes it into. So there's damage done both by pulling things out of where they came from and by slamming them into other stuff as they wash downstream in the flood. You also have pollutants in floodwater. So they strongly recommend, if you are in a flooded zone, do not go into the flood water. So even if it's a river that you might, on ordinary days, like go swimming in or something, once it floods, there's the potential for there to be a lot of gnarly chemicals in that water, because you can see there in the picture, it's flooding people's basements and lower floors. And people have all kinds of stuff in there that you probably don't want to be swimming in a bathtub full of, right? There might be, herbicides for their lawn that they kept in their house. There might be paint. There might be, household cleaners that are in there. There might be gasoline from cars. There's, all kinds of stuff that we store outside of a stream that now gets mixed into that water as it flows down. So that's probably not good for you. So, emergency managers strongly recommend that you do not enter floodwaters. Don't go wading in those floodwaters. Make sure that if you have to go someplace that's flooded, make sure that you're going in a boat, but really you should just wait for the floodwaters to go down before you try to return to those flooded areas. There's also just the potential that there's all kinds of stuff that you could step on or trip over, because you can see those waters just have a lot of sediment suspended in them, right? They're, that light brown color there, you can't see what you're walking on if you're trying to swim or wade in those floodwaters. So there's lots of dangerous things lurking in there that could do a lot of harm to you. Then that water is going to do a lot of damage to your property and other sorts of structures. So all those people whose houses are getting basically soaked in water for several hours to several days, depending on how long that flood lasts. So anything in your house that can absorb water is going to absorb an awful lot of it. And so that can do damage. It's really obvious if you've got things like, wood and carpets and so forth. Those often have to be just torn out and thrown away because they've gotten too soaked with that dirty floodwater. Even things like concrete and stone and brick, they are slightly porous. They can absorb some of that water, and it can cause some problems if they soak for too long in that floodwater. So it's important after a flood that you or a restoration crew get in there, remove all the stuff that is too damaged to be repaired, and get everything dried out correctly using the correct kinds of airflow and so forth to make sure that you dry things out, that mold doesn't grow in things that are wet, etc. So a house, even if a house is still standing after a flood, there may have been a lot of damage done to it by those floodwaters, and that house may need significant repairs, or even in some cases to be torn down and rebuilt. And then finally, floods can accelerate erosion and deposition. And that's going to be our big topic for next week. We're going to talk about erosion and deposition. So for now, just sort of keep in mind, you've got floodwaters coming along. They're hitting places that don't normally get water in them. They're coming along with a lot of energy, and so they can erode a lot of soil, sweep it away, and leave that soil somewhere else. So those are all the different kinds of hazardous effects that a flood might have. So now let's talk about how we can measure a flood. How big is a flood, and how big of a flood do we have to worry about and plan for in a particular place? So there are a few different things that we might measure about a flood. So one thing we might try to measure is the flood's discharge. So the discharge is the rate at which water moves past a certain point in the channel. So these are all measurements of the flood at a certain spot, because the same flood event might have different effects and different sizes at different parts of the same river. But at a given point, if you measure the rate at which water is moving past a certain point, and usually be in something like cubic feet per second or cubic meters per second in metric, then you're measuring the discharge. The discharge is essentially the flow, right? If we think of each stream as being a little flow within our hydrological system, right? And so when we were looking at the whole hydrological system, we were just adding those all together as sort of one big total flow, but we could break that out. Each stream has its own flow, its own movement of water from its source stock to the stock that it flows into, the ocean or a lake or whatever it's flowing towards. If we measure the size of that flow, that is the discharge, that is the amount, and then we can compare that to the average discharge of that stream, and that tells you how much bigger than normal that flood was. So that's a nice number to have. The catch is that is much harder to measure. So it takes a lot of sophisticated equipment to accurately measure the discharge rate of a stream, and that equipment can often be damaged during a flood. You've got all this excess water with all this extra energy coming down that often damages that equipment and destroys it right when we want that data the most. So we often don't have good discharge numbers, or if we have discharge numbers, we're kind of trying to calculate them or estimate them from other numbers that are easier to measure. A number that is much easier to measure is what we call the stage of the flood. And the stage is the height of the surface of a stream, measured in either feet or meters, above a sort of normal reference point. So we have the average water level of that stream. That's kind of our starting reference point. And then we measure how much higher is the top of the stream above that reference point. And so that's real easy to measure because all you need is a measuring stick. And you'll actually see flood gauges painted on the sides of like bridge abutments. Anywhere you have a vertical thing going down into a stream, you could just paint numbers on it. And then anybody that goes by can look at that and see what stage the water is at. So super easy to measure as compared to discharge. Obviously, if you want that data to be collected continuously and like entered into a database, you need something a little more sophisticated. And there are flood gauges that will record those measurements. But if all you want is a way to look at it and see what stage we're at, all you need is to paint some numbers on the side of a bridge. So stage is real easy to measure. The problem with measuring floods by their stage is that there's not a neat linear relationship between discharge and the stage. So with the discharge, we're looking at the actual volume of water that is coming through. With a stage, we're looking at how high the surface is. And so if you think about the same volume of water, if it goes through a valley that is very broad and wide, that's only going to raise the stage a little bit because that water is spread out across a really wide valley. If you get that same amount of water flowing through a valley that is very steep and narrow, like a little canyon, that's going to raise the stage a whole lot because there's not a lot of room for that water to go. It has to pile up vertically. So there's not a simple linear relationship between discharge and stage. The more discharge you have, the higher the stage is going to be. It is directional like that, but the relationship, how much discharge leads to how much of a stage increase is going to depend a lot on things like the topography, the shape of the valley that our flood is happening in. Then another important piece of data that we often have about floods is their peak. So the peak is the highest stage or highest discharge, whichever we have information on, but the highest one reached by a stream during a given flood event. So generally with a flood, it will start with, at your sort of normal or average level, it will rise, it will hit its peak, and then it will come back down. So a typical or normal flood event is up and then back down. So if we know that highest level that it got to, then that is the peak of that flood. And we often talk about floods in terms of what their peak is. And we, talk about how often do we get a flood with a certain peak level. And so in talking about the size of a flood, you often hear people use terminology like a 100-year flood or a 500-year flood. So measuring floods in years. This year measurement is what's called a return interval. So the return interval is that year statement about a flood. But the phrasing it that way can be a little misleading. So I want to talk about return intervals because you'll encounter that language. That's a language that's commonly used in weather reports. It's used by the government, etc. So you should be familiar with what this language means, even though I think, and a lot of hydrologists think, it kind of misrepresents what's going on and gives people some incorrect impressions. So what a 100-year flood means is it's a flood whose peak has a 1 in 100 chance of occurring in a given year. Okay, so a 1 in 100 chance of getting a flood at least that big, we call that a 100-year flood. So we can also describe that chance as a percentage, right? 1 in 100, that's 1%. So a 100-year flood is a flood that has a 1% chance of happening in a given year. And we refer to that percentage as the exceedance probability. So that's the probability that a flood greater than that height would occur in a given year. And so there is an inverse relationship between the return interval and the exceedance probability. Right? So a 2-year flood means a flood that has a 1 in 2 chance of happening in a given year. That's a 50% exceedance probability. So you would get a flood at least that big. It's a 50-50 chance whether you get that in a given year. A 5-year flood has an exceedance probability of 20%, etc., all the way up to, on this chart I show, a 500-year flood means an exceedance probability of 0.2%. So the 100-year flood language can be misleading because it could imply that there's a regular cycle, that you get a 100-year flood every 100 years, and that if it's been a while since we had a 100-year flood, then we're kind of due for another flood of that size. But that's not the case. So flooding events are random. So we know we have a certain probability of seeing a flood of a certain size, but it's totally random whether we'd actually get that flood in a given year. And it has no relationship to whether we've seen that flood before. In the same way that if you have a regular 6-sided die and you roll it and you get a 3, and then you roll it again, that next roll has the same probability of coming up 3 again that it did on the first roll. The fact that you've already rolled a 3 has no bearing on what you're going to roll the next time. So the 100-year flood language can be a little misleading. It does not mean that we get one on a regular cycle of every 100 years. What it means is that there's a 1 in 100 or 1% chance of it happening in a given year. And so that means on average over the long term, we'll probably see about 1 every 100 years. But this is all calculated from a database of past flood levels. So this is all about using past data to try to predict what we'd see in the future. So if we look at our past data and we find that within, say we have 100 years of data and we've had 1 flood of a certain height and nothing else bigger than that, then that becomes our 100-year flood. And if we look at that past data and we see that we've had 2 floods of at least a certain height, that height is our 50-year flood, or 2% chance of happening every year. So let's look at how we might get this out of some actual data. And this is something you'll be doing in your activity for this week. And I've posted another video on D2L where I go through this sort of step by step within Excel. So in the lecture, I'm just going to give you the big picture of how this works. So if we want to calculate our return intervals for floods, what we're going to do is first we're going to get a database of the biggest flood each year. So the peak of each year's biggest flood for as many years as you can for the place whose return intervals you want to calculate. So the more data you have, the better. The longer the history of flood measurements that you can work with, the better. So in my little toy example here, for a river in Oregon, I'm only dealing with 11 years of data just as an illustration. Ideally, you'd want quite a bit more data than that if you were going to get reliable results out of that. But you get your database of the biggest flood each year for as many years as you can. And then you're going to rank your floods in your database from the highest to the lowest. So you give the year with the biggest flood a 1, then the year with the next biggest flood gets a 2, the year with the next biggest flood gets a 3, and so on until you rank them all. So you can see on this data here, in this case, we have discharge data in cubic feet per second. So our biggest flood was the one in 1999 at 40,000 cubic feet per second. So we called that 1. Then our next biggest was 1996 with 34,700 cubic feet per second. So that's our number 2, all the way down to our year that had the smallest flood, which was in 1992 at 10,800 cubic feet per second. So that gets our lowest rank of 11. Then for each year, you then apply this formula, Ri equals n plus 1 over m. So Ri in this formula, sorry, Ri in the formula is the return interval. So that's that number in expressions like a 100-year flood. And the return interval is equal to the number of years of data plus 1. So in this case, n was 11. We have 11 years worth of data, so n plus 1 is 12. So it's going to be 12 divided by the rank for that year. So the rank that we've given each year is the denominator in that. So we divide 12 by that rank, and that gives us our return interval. And so what you can see there is 1999, our year with the biggest flood, since that was we have 11 years of data plus 1 is 12. Divide that by the rank of 1. 12 divided by 1 is 12. So that becomes a 12-year flood, a return interval of 12 years based on our 11 years of data. Then we get our second biggest year. Okay, so we're taking that 12 divided by 2 gives us 6. So that becomes a 6-year flood, a flood with a return interval of 6 years, and so on down those numbers. So once we get the return intervals, one thing we could do is we could turn those return intervals into exceedance probabilities. Right? So if it's a 1 in 12 chance of having a flood that big, we could divide 1 divided by 12 to get a percentage for the exceedance probability. Another thing we could do is we could use this data to extrapolate the return intervals for floods that might be bigger than the ones that are in our database. So we've got 11 years of data here. That probably does not encompass the biggest possible floods that could ever be seen at this location. We want to extrapolate into possible bigger floods that might have happened before our data that we have and that might happen in the future. And so we can do that by graphing them. So we can graph our return interval in this case, on the vertical axis, and our discharge amount on the horizontal axis. And one thing you'll notice here in this diagram is I've used a logarithmic scale for the discharge. Because just like with earthquakes, that the bigger the earthquake, the rarer it was, the same thing happens with floods. The bigger it is, the rarer it is. And that occurs along a logarithmic scale. So a bigger flood is going to be 10 times less likely, or 1/10 as likely as a smaller flood. So when we're using that logarithmic scale, that puts our points into roughly a straight line, which makes it a lot easier to extrapolate into the future. So in this case, I plugged this all into Excel where I made this graph, and so Excel will calculate the best line going through that data. And so we can get an equation for that line. You can see the equation on the graph there. X equals 7 point some stuff minus 68. So we could use that equation to calculate the exact expected discharge for a given return interval. Or we could simply eyeball it off the chart by extending that line out farther. So our biggest return interval in our data was 12 years, but we can extend that line out. And so we can see that, say, a 15-year flood at this location, based on the existing data, we would expect to have something around 100,000 cubic feet per second of discharge, whereas we'd get up to about 1 million cubic feet per second of discharge when that line gets up to, looks like probably about 35 year flood. So we can extrapolate out to those bigger floods that aren't in our database by looking at the data that we do have. Okay, so that floodwater is, in the cases we're talking about here, coming from runoff from precipitation. So we're focusing on precipitation-driven floods here. So how do we connect the amount of precipitation that's falling to the floods that might cause as that water gets into the stream? Well, the amount of water going into a stream is going to be a function of several factors. So it's going to be a function of the intensity of the rainfall. So how much rain is falling within a given amount of time, right? So how heavy is that rain coming down? It's going to be a function also of the drainage area. So if you have a lot of area all draining into one stream, that's going to be a lot of water coming into that stream. If that stream only has a very small drainage area, less water can get to that stream. And then third, something called the runoff coefficient. So the runoff coefficient is a measurement of what percentage of the rainfall that falls within that drainage area actually makes it to the stream. Because sometimes that water will fall on the ground and it will run off into the stream. Other times that water won't make it. It will, for example, get absorbed into the soil, and so it doesn't make it to the stream. So that runoff coefficient is going to be less than 1. A certain percentage of that rainfall is not going to make it into the stream. And that runoff coefficient is affected by a whole host of other factors. So there's a whole lot of things that affect what percentage of the rain that falls within a drainage area actually ends up running off into the stream. So it's going to include things like the slope of the land. The steeper it is, the quicker stuff is going to run down into the stream. The surface cover. So do you have paved surfaces? Do you have surfaces with a lot of leaves on them? Do you have surfaces with bare earth or with rock or whatever else is the surface of your land? You have the soil type. Some soils absorb a lot of water very easily. Some don't absorb very much water. It's also going to be affected by drainage infrastructure. So if your water hits some sort of a storm drain or a pipe that's going to whisk it right off to the stream real quick versus having to run across the land and potentially, get soaked in or something along the way. So all of those factors will affect, from the same rainstorm in the same drainage area, how much water might make it into your stream. And so human activity can have a big impact on runoff coefficient, that we can alter a lot of those factors and change how much water runs off into our streams. So one very broad generalization that we can make is to compare urbanized areas to natural areas. So again, very broad sort of generalization here. A natural area is one that hasn't seen a lot of development. So for example, our land cover is going to be mostly trees or grasses growing in soil. Whereas an urbanized area is going to have lots of impervious surfaces. It's going to have things like building roofs and pavement from roads and parking lots and that kind of thing. And what we find is that urbanized areas have higher runoff coefficients. More of that water is going to run off those areas towards the streams. And so in urbanized areas, our streams fill up bigger and faster than they do in more natural areas. So you can see that on the graph there. So we get some rainfall, and that rainfall starts to run towards our streams in an urbanized area. So they're describing this as after. So like after an area has become urbanized, after we cut down the trees and replace them with parking lots and stuff, that water is going to move very fast across that parking lot, right? Water flowing across the parking lot moves a lot faster than it would move across like leaves on the floor of a forest, sorry. Um, that water is going to move real fast, and a lot more of it is going to go because once that water is running across pavement, there's basically nowhere else for it to go. It's got to run off, whereas water running across plant material and soil is going to partially soak in as it goes. So the peak of our stream is going to happen earlier, and it's going to be higher in an urbanized area than in a more natural area. So urbanizing areas tends to make our floods bigger and faster than they would be otherwise, even with the same precipitation. So even if the precipitation amounts that we're getting are the same, if we have paved over everything, then we're going to get bigger and faster floods than if we still had our natural ground covers like trees and grasses and so forth in place. So now let's look at some of the things we can do to manage floods, some of the things we can do to cut down on the risks posed by floods. So you'll remember all of those harmful things from floods that we talked about a little earlier. What can we do about that? Well, one thing we can do is to build levees. This is basically just a wall that we build to block floodwaters. So if we're worried that floods are going to come up on us, build a wall to hold that water back. So that's a pretty straightforward kind of thing to do, and there are lots of levees all over the place. They're a very popular form of flood protection. You can see one in action there in the picture, where if you can see that the water level on the right side of that levee is quite a bit higher than that road, and the houses, you can kind of see the driveways coming off it there, right? Those houses on the other side are below where that water level is, but the levee is protecting them from those floodwaters. Some of the downsides to levees are first that it can be catastrophic if the levee is breached or overtopped. So all of those houses are doing great now so long as the floodwaters are lower than the top of the levee. But if the floodwaters were to get high enough, and it looks like in this picture they're only a few feet short of the top of that levee, if the floodwaters were to continue to rise and were to come across the top of that levee, then you would get water rushing down that levee in potentially a pretty damaging way for the people living on the other side, or if something were to cause that levee to break or burst. So if the levee is, say, poorly maintained or was poorly built in the first place, the pressure of that water building up against it and water soaking into that soil may cause that levee to fail, to break, and then you get this high energy rapid rush of water through the broken levee onto everybody that was sheltering behind it. So the levee is great up until the moment it fails, at which point it is probably worse for you than if the levee had not been there in the first place and the waters had risen more slowly. Levees also tend to funnel floodwaters towards vulnerable areas because not everybody can afford to build as good of a levee or build any levee at all. So we very often find places where, say, wealthier communities with more resources have built themselves some nice levees, and so they're keeping the water from flowing in their direction, and so that just pushes that water towards wherever doesn't have a levee, which might be, say, a poorer community that doesn't have the resources to build a nice tall levee. So the floods then experienced by the people without the levee are worse, right? If you imagine, for simplicity's sake, imagine a river that just has two sides to it. One side builds a big levee and the other side doesn't. Well, now the side without the levee is going to get double the floodwaters because they're getting the floodwaters that would have come to them, plus they're getting the other side's floodwaters that are being held back by the levee. The levee is pushing all the floodwaters to one side, so they can tend to funnel floodwaters towards vulnerable areas if the building of levees is uneven at different points of the same stream experiencing the same flood. And levees can encourage development in dangerous areas. So all those people built their houses right next to that levee because they felt safe. They felt like the levee was protecting them, which means they're now at high risk if something were to happen to that levee. So it can encourage kind of complacency, people building in areas that are dangerous, people not taking other precautions because they're like, oh, the levee will save me. And then it doesn't, and then they're in big trouble. Another thing that you can do to protect against flooding is through architectural choices that are meant to protect you from flooding. So the example that I've got here is putting a house up on stilts. So in a lot of areas of the world where flooding is common, people will raise their houses up on stilts. So that way you have no basement to get flooded. And those stilts are really easy to clean and repair once the floodwaters have come through. It's not like, the basement of a house might keep a big pool of water in there, doing further damage to your house, soaking into everything. But if it's just, that kind of open space with those poles in it, that's real easy to make sure that it's in good shape after the flood has gone through. So that'll keep that house nice and safe so long as the floodwaters are lower, the flood stage is lower than the height of those stilts. So we're designing buildings to resist flood damage. And there are a bunch of other architectural things that can be done to make buildings and infrastructure flood resistant. So for example, you can build walls and piers that would deflect objects that are being brought down by a flood. So if you're worried about floodwaters moving at a high speed, bringing things that are going to crash into your house and damage it, if you build some sort of a wall or a pier upstream of you to deflect that, that would be another example of flood-resistant architecture. So there are various things that you can do. Downsides here are, first, that it can be costly for new construction. So when that house was built, it was more expensive to build it up on those stilts than to build it flat on the ground. And it may be effectively impossible to retrofit existing buildings. So if that house had already been built without the stilts, it may turn out to be essentially impossible to raise it up and put stilts in it after the fact. So then you either can't do it, or you would have to knock the house down and rebuild from scratch. And so trying to do that on large scale, protect an entire town from flooding this way could be incredibly expensive and even impossible. And then there are architectural trade-offs. Anytime you choose to do a certain thing architecturally, there are other things that you have to give up on. So for example, these people don't have a basement, and basements can be pretty useful. I get a lot of use out of my basement because I live in a non-flood prone area. And so it would be I would lose something if I had to put my house up on stilts due to flooding, because I wouldn't have that basement anymore. Another thing that can help us manage floods is wetlands. So you can either preserve natural wetlands or create artificial wetlands to absorb floodwaters. So if you've got a flood rushing down a stream and it hits a swamp area, a wetland area, that water is going to spread out across that wetland, is going to get absorbed by the soils and plants in that wetland. It's going to slow down because it's now got a lot of friction to move through as it passes through that wetland. And so that's going to take the edge off that flood. It's going to reduce the amount of flooding, both in terms of volume of water and energy of the water that come to anything that's downstream of those wetlands. And it's doing this, it's essentially altering the runoff coefficient, that this water flowing into the stream is now being held back. It's not all going into the stream downstream of the wetland. And a lot of places learned this the hard way, because throughout the 19th and 20th centuries, there was a big prejudice against swamps. Swamps were seen as a bad thing. It was unproductive land. It was mosquito breeding grounds. It smells bad. And so there were a lot of efforts to get rid of wetlands, to channelize rivers. So rather than spreading out into a big wetland, they would stay in a nice narrow channel. Sometimes they'd put up, concrete walls to the channel to keep all the water in one place and dry out the land to either side so that you could build on it, you could farm on it, etc. So there are big efforts to do this all across the United States and other parts of the world. And we've learned the hard way that the destruction of these wetlands leads to bigger and more dangerous floods, because we no longer have these wetlands acting as kind of a sponge to soak up that flood water and reduce the water volume and the energy of that water going downstream. So now we have laws in place to prevent development in wetlands, to preserve the wetlands that remain, and to restore wetlands. So we will often deliberately build new wetlands, create wetlands to serve this kind of function. So wetlands can do a lot of services. They also tend to clean the water. So if that water is carrying with it sediments and pollution and all kinds of other stuff like that, that will tend to get filtered out in the wetland, and you'll have cleaner water going downstream. So an extra bonus. So wetlands are, in my opinion, as an earth scientist, really awesome, and we should have more of them. But I do recognize that there are trade-offs for relying on wetlands for flood management, because all that land that you're keeping as wetland, well, that's land that's not available for other kinds of development. So you can't build houses on it, you can't farm on it, etc. So you're sacrificing a lot of land that may be in kind of optimal locations. And there is still that prejudice against swamps. People still have a negative view of swamps and bogs and other kinds of wetlands. You know, even those names sound really negative, right? Swamp sounds like a bad thing. And that's why we often say wetland in this context, because wetland is a nicer sounding name, and it won't activate those negative associations people have with them. Another thing we might do to deal with floods is insurance. So the basic idea behind insurance is that everyone pays in a little bit every year, right? You have your premium, you have your payment that you have to make on your insurance, which is then used to make payouts to anyone who actually suffers a negative consequence. So if you think about car insurance, for example, you pay a little bit every year in your car insurance policy, as does every other driver insured by your same insurance company. And then the insurance company keeps, I mean, they use some of that money to like pay their agents and so forth, but they keep most of that in the bank so that when somebody does get into a car crash and needs a whole lot of money all at once, they have that money that everybody's been putting a little bit in all along, and they can use that to pay out for that big insurance claim. So flood insurance works the same way. Everybody pays in a little bit on an ongoing basis, and so then once there is a big destructive flood, the people that need big payouts because they need to totally rebuild their whole house, for example, draw on that money. That's the basic idea behind insurance. There is a federal requirement in the United States that homes located in the 100-year floodplain must have flood insurance. So I don't have flood insurance on my house because I'm located way up on a hillside. And so the likelihood of a big enough flood happening that would flood my house, just the volume of water that would have to be going down the Ohio River to make that river get high enough to get to my house, is just sort of astronomical. It is highly unlikely to ever happen during my lifetime. So I actually don't have flood insurance. But if I were living down close to the river, then I would have to carry that flood insurance. It would be both a good idea, a good investment for me, so that I had that backup and I knew I'd get that payout if there was a flood, and it could be a federal requirement. I would not have been able to get a mortgage for my house without having flood insurance if I was within the federally designated 100-year floodplain. So the 100-year floodplain is the areas that would be flooded during a 100-year flood. So we figure out what the 100-year flood is for a given stream, and then we can look at our topographic maps and say, well, if we reach this stage, right, this many feet above the usual level of the water, what areas would that flood, right? How much higher would that water be, and what areas are below that in elevation? That's our 100-year floodplain. And so the image here comes from the federal flood mapping and shows areas around Slippery Rock that are within that 100-year floodplain. So that is the light blue area here. And so if you look at that map, you'll see the borough of Slippery Rock there kind of in the middle, and then our campus in the kind of darker golden color there. So nothing within the borough or within our campus are within that 100-year floodplain. But you can see it's down there in Worth Township along Wolf Creek. So if you can remember when you were looking at the topographic map in an earlier lesson, and we looked at Wolf Creek. So it's a small little creek, and it's flowing through this floodplain that would get flooded. So there are a number of houses down there. If you've ever driven on Route 108 out towards the highway, and you go past where Wolf Creek is, kind of the lowest point as you're going along the highway, you'll know that there are a bunch of houses down there. And if we get a big flood, then those houses are at risk of flooding. And that actually happened a few years ago. So for about a week, every time I drove to and from work, because I was coming in off that highway, I would drive past those houses that are right along Wolf Creek, and they had several feet of water in all of their yards. And I don't know any of the people that live there, so I can't tell you, any direct stories about the damage it did, but it certainly looked like a number of those homeowners were going to have some significant damage from that flood. And so hopefully they all had their federally mandated flood insurance to help them to cover that. So insurance can help pay for rebuilding after a flood. And it's often supplemented with federal, state, and private charity aid. So after a big flood, often either the federal or state government will step in and give additional aid money to people because sometimes your insurance policy doesn't cover everything that you would need to get back on your feet. And there are charities, people will start their own, like a GoFundMe or something, and then there are organizations like the Red Cross that will gather money and use it to help people out. So those serve in some ways kind of the same function as insurance, right? Because you're paying your taxes into the government. You may be making donations to charities when they're helping somebody else out, and then then in the future maybe you'll get helped out by that same charity. So it's sort of the same idea as insurance. The downside to all this is that it can encourage development in dangerous areas, because if you are like, well, I have flood insurance and I know the government is probably going to give aid if we get a pretty serious flood, then it's not so bad to build in a floodplain that might otherwise be an attractive place to live. It's nice to live right along a river or something, and so it might encourage people to build in areas that are dangerous rather than staying back from the areas likely to flood. And then a final approach we might take to dealing with floods is evacuation. And so when I'm talking about evacuation, I'm talking about both temporary evacuation in response to a specific flood warning. So, you see that it's raining really hard and you're worried about a flood, or maybe you get an alert from the National Weather Service that there's a flood risk, or even they've detected floodwaters starting to move down your stream, and they say you need to evacuate, so you can temporarily leave to get out of the path so that at least you aren't harmed by that floodwater. You might take some of your important belongings. You drive your car away, you take your important documents, your valuables, and your pets, so that can preserve those things from damage that flood. But there's also more permanent relocation. So some areas that have been repeatedly hit by floods, and so where the flood hazard is pretty high, there are efforts to move people out of those permanently, to say that, look, this area is just too dangerous for people to live in. The flood risk is too high. We're going to permanently remove everybody from there, which may be a decision that people make individually. They just decide, okay, I'm going to move out of here because I keep getting flooded. Or it may be something that's done on kind of a government level, where the government decides, all right, we got to get rid of this town. We're going to relocate you all someplace else because it's just too expensive. It's too much risk to people's lives to be continuing to live in this area that we now understand to be much more hazardous than maybe it was, or maybe that we realized it was back when people first moved in there. With evacuation, though, it can be hard to get the message out, especially to some of the most vulnerable people. So if you're imagining, National Weather Service is sending out this alert about a potential flood, and you think about who might be some of the people that might not get that message, or might not get it in time to act on it. It could include people who are very poor, and so maybe they don't have current cell phone service, and so they don't get the alert. It could include people who are living in extremely rural areas, where again they don't get, they're not connected to the networks that they'd get that warning through. It could include people who don't speak English fluently. If the alert is sent out in English and you're not an English speaker and you get this thing, you don't know what those words mean, and so you might not be able to act on that warning quickly. So it can be hard to get the message out to people, especially those who are potentially most vulnerable to that flood. And then even if people get the message, they may not have the resources to evacuate. So if you've got a car that's in good working order and has gas in the tank, it's comparatively easy for you to hop in the car, grab your pets and family members and drive away to some place that is higher ground. But if you don't have a car that's in good working order, for example, right, because maybe you are just too poor and can't afford to keep your car in good repair, you might not be able to get out of there. You may have responsibilities that keep you from leaving. So for example, if you're a caretaker for children or for an older relative, that adds a lot of complication to your ability to evacuate because you have other people that you need to take care of and bring them with you. And that may be complicated if you have to go fetch them from other locations or if they have special needs. So like, you're caring for an elderly relative who needs an oxygen tank. Well, now that's an extra complication. Or if they use a wheelchair, now you got to make sure you can get the wheelchair correctly loaded into your car that's not built as a wheelchair van or something. And we actually find that when we look at who successfully evacuated from major flooding events, like, for example, Hurricane Katrina in New Orleans. So the hurricane came along, there was massive flooding, there were levees that broke in many of the neighborhoods and contributed to this flooding. And so people were warned ahead of time. We knew the hurricane was coming. Some people just not able to evacuate. They didn't have a vehicle. They didn't have a place to go. They had people that they had to help to evacuate. We found that there was a big difference in income level. So richer people were more likely to successfully evacuate. It's a big difference with respect to race. So white people were more likely to successfully evacuate than black residents of New Orleans. And there was a big difference in gender, so that women were not able to evacuate as easily because they're more likely to have these responsibilities. They had to go get grandma, they had to go get the kids or something, and so that delayed and complicated their evacuation. And then with any evacuation, there's always a uncertainty to it. We never know exactly what that flood is going to entail when it comes to you, especially if we're trying to warn people well ahead. So before floodwaters have started to rise, but we project that there's going to be all of this rain because we can like see the storm forming or something. So you have to balance the risks and costs. So on the one hand, if you don't give an early and strong enough warning, then people are going to get flooded and they're going to suffer a lot of damages from it. They're going to be mad that they weren't given adequate warning. On the other hand, if you warn them too early and it turns out the flood is not that big, not that destructive, then that's expensive for all those people who had to disrupt their lives, maybe spend a bunch of money on a hotel room or something to get out of there. And then they're going to be mad that they were evacuated for no reason. And they're going to not trust future evacuation warnings. They're going to be like, well, last time they said to evacuate, it turned out to be nothing. So why should I evacuate now? And then you get a boy who cried wolf kind of situation where people start to ignore the warnings because they haven't panned out in the past. So this is actually a really complicated thing for emergency managers to figure out, is at what point are we sure enough that the flood is going to be destructive enough that we need to get that warning out there so that people will successfully evacuate, versus when is it going to undermine our credibility by giving people a warning that they didn't really need. So that is some of the basic information that's good to have about flooding. You'll dig into some of this in more depth in your activity, and I will see you next week.